Here we learn about the mean value theorems. These theorems say that if we have a function f of x which is continuous on the interval ab, on the closed interval ab, and differentiable on the open interval ab. So this is to say that the graph, you can draw it without lifting the pencil. And the graph has no like sharp point like this or cast point. So every point on the graph, you can draw this tangent line here. So you can compute the derivative at every point on the graph. If the function satisfies the condition of the theorem, so we have two conditions, continuous on the closed interval AB and differentiable on the open interval AB, then there must be a point between A and B such that f prime at C equal to f of A minus f of B divided by A minus B. Here I draw an example. The graph here is a graph of a continuous function on the closed interval AB, and it is differentiable on the open interval AB. So at every point we can do the derivative and compute the slope of the tangent line. F prime at C is the slope of the tangent line at the point C, FC. FA minus FB over A minus B is the slope of the secant line joining A and B. So this is to say that there exists a point on the graph. If you draw the tangent line, then that tangent line will be parallel to AB. That's the theorem say. So in this example, I have multiple of such points C. So here another example. If we draw the graph, say, now I just draw this simple graph, A and B. The function f of x is continuous on the closed interval AB. The function f of x is smooth in the case, so the function is differentiable on the open interval AB. Then we have a secant line, the line joining the two endpoints of the graph here. On this graph, I can find a point, at least one point, so that the tangent line at that point is parallel to the secant line. So let's see where that point is. It was here. So this is the first point I have. This point P has a coordinate C, comma f of C. And in this example, I can even find another one. Draw the line that is parallel to the secant line. So here I have the second tangent line, which is parallel to the secant line. This one also gives me the point C in the theorem. F prime of C equal to the slope of the secant line. This is our secant line. So here we have Q. Let's call it C2, comma F C2. So here one example of using the mean value theorem. They give us a function f of x equal to this one. So obviously this function is continuous on the closed interval. In this case is minus 2 to 2. It is differentiable on the open interval, minus 2 to 2. And therefore it does satisfy the condition for the mean value theorem to hold. So the first question is yes. If it does, find the point C between minus 2 to such that we have this one. So this is the slope of the secant line, the line joining the two endpoints of the graph. One corresponds to minus 2, comma f of minus 2, and the other one 2, comma f of 2. We say that f is continuous on the closed interval -2, 2. F is differentiable on the open interval -2, 2. And thus these are two conditions of the mean value theorem. So F satisfies the condition of the mean value theorem. And by the theorem, we know that there is C between -2, 2, so that F prime of C equal to F of 2 minus F minus 2 over 2 minus 2. Now we compute that F of 2, so compute that here, F of x equal to this. So F of 2 and F of minus 2 will be 2 to the fourth, 2 times 2 square, 7 times 2 minus 2. So we have 16 minus 8 plus 14 minus 2. So this is 8, 12, so we have 20. And the second one, we need to compute F minus 2. F at minus 2, so we have minus 2 to the fourth, so 16, minus 8, minus 14, minus 2. 8 minus 16, so we have minus 8. And therefore this one is 20 minus 8 over 4. 28 over 4, 7. There exists C such that F prime at C equal to 7. Now we find C. We are trying to find C. We will find C between -2, 2, such that F prime C equal to 7. So just compute F prime of C and let it be 7. F prime at x, 4x cubed, 2 times 2x plus 7. So 4x cubed, 4x, 7. So we need C. We need to find C such that this one equal to 7. So this means 4x cubed, 4x equal to 0. 4x, x squared minus 1 equal to 0. So x equal to 0 or x minus 1 equal to 0. X squared equal to 1. So x 0, 1 or minus 1. So we have three possible values here. For f prime at the point x equal to 0, so we have 0, 1, minus 1, and all of them are on the interval -2, 2. So these are our values for C. C equal to, or C belongs to the set 0, 1, minus 1. Now let's try one example where we couldn't use the mean value theorem. Say example 2, we have the function f of x equal to x 2 over 3. So f of x is continuous on -1, 1. However, it is not differentiable on the open interval minus 1, 1. Differentiable. So let's compute that f prime of x, 2 over 3 x, 2 over 3 minus 1, 2 over 3 x minus 1 over 3. So we write as 2 over 3 cube root of x. So you see that this is only well defined for x non-zero. So f prime of x does not exist when x equal to 0. So this is not differentiable. So there's one point here, 0 is not differentiable. And therefore we cannot use the mean value theorem. Do we have c between minus 1, 1 such that f prime of c equal to f1 minus f minus 1 over 1 minus 1. So does f satisfy the condition for the mean value theorem to hold? The answer is no. This is because f is not differentiable on open interval minus 1, 1. And the second one, do we have the value c between minus 1, 1 so that we have f prime of c equal to this. So let's see, f equal to x power 2 over 3, f of 1 equal to 1. So 1 power 2 over 3, f of minus 1 power 2 over 3 over 1 minus 1. So this is 1 minus 1 over 3, which is 0. So the question asks us whether we have c between 1 minus 1 and 1 so that f prime of c is 0. We know that f prime of x equal to this one. And therefore no value c so that this one can be 0. No c between minus 1, 1 so that prime of c equal to 0. So we see that in this case, for this function, we cannot use the mean value theorem because it doesn't satisfy the condition for the theorem to hold.